today, we are honored to have President and CEO of Xilinx, Mr. Victor Peng, to be our executive keynote speaker. So Victor Peng is the President and CEO of Xilinx and served as the board of directors. Peng has more than 30 years of experience in semiconductor industry. He became the CEO of Xilinx from February 2018. And Peng has rolled out plans for a transformative to address new markets with new technology and their new adaptive compute acceleration platform. Now let's welcome Mr. Victor Peng to give us the speech.
Hey, good evening. It's a great honor and a great pleasure to be here to share our view in Xilinx of the AI era. I think that it's rare that you have a situation where there's a tremendous amount of hype around technology, but I think the hype is really real. And I think it's also interesting to note that even though there's been so much talked about and real applications being deployed, we're in the really, really early stages. And I think that's a really important thing to keep in mind. And one of the perspectives we have that's maybe a little different than other people that you've heard speak about AI is that we believe that there's a new heterogeneous compute architecture that's going to play a very large role in AI. That's called this adaptive compute acceleration platform. And the reason for that is really quite simple, right? There's a tremendous explosion of data that's being generated, and we have to process that, and get factors of improvement, tens to hundreds of factors of improvement. And the only way to accomplish that is to have heterogeneous architectures, and I would submit that you need adaptability. Because when you have very, very large-scale distribution of intelligent agents, for them to be resilient and convey all this data and processing over the long haul, you really need adaptability. Just like organic species in nature need to be adaptable to survive over the long run. So intelligent connected devices are becoming pervasive. I bet everybody in this room use an intelligent device today, whether it's your smart speaker, your phone, driving in a number of the automobiles, or even in the office. There's already deployment of very intelligent devices. And it used to be in the old days that, right, just like 5 years ago, I would say, that a device was considered intelligent if it just had a processor or microcontroller. Now that's no longer the case. Today and in the future, a device is intelligent if it's going to have multiple different heterogeneous compute engines and support multiple deep neural networks. And again, the torrents of data being generated have to be processed essentially in real time. So what's really important is not only do you need higher performance, but you need low latency. And ACAPs are really perfect for dealing with processing extreme amounts of data in real time, and also handling a diversity of different types of neural networks, a diversity of different types of applications. Just a few weeks ago, we had our developers forum called XDF in San Jose. Jumped ahead. Okay, there we go. And these are just a few highlights from that forum. As you can see, we had our customers that are using our technology for a gamut of different applications. Everything from 5G infrastructure to cloud computing, lots of video processing, and also autonomous driving. 4 out of these 6, this is just a sampling, but 4 out of 6 of our major customers that spoke at XDF are related, at least in part, in several cases, heavily in AI, right? Be that AI in the cloud, or such as IBM. IBM actually wasn't showed here, but IBM Watson, yeah, there you go. IBM Watson was showing there. Amazon's Neo, SageMaker, all of that was all presented, as well as 2 fully autonomous driving applications. And again, right now, the thing to remember is it's still early stages, right? To date, the vast majority, this is showing market size, the vast majority of AI revenue is actually still all from training. It's just the very, very early stages of inference deployment. And what you can see over time is, in not very long period of time, that the inference market is going to be factors larger than the training market. What's also interesting to note is a lot of that inference is really going to happen at the edge. So, you know, and when I say edge, also you hear me refer to endpoint devices. So you can think of an endpoint device like a single sensor, a single camera, and, you know, where the edge could be something like an aggregation point, be that, you know, some sort of small server, or it could be like a car, right? So, you know, I think this sustaining this growth is going to take these heterogeneous silicon architectures that I talked about, and including domain-specific architectures. So, and the reason for why DSAs, domain-specific architectures, together with other maybe traditional computing is going to be needed is simply because to keep up that exponential growth, right, you're going to be processing exponential growing data, and you need tens to hundreds, and even over the long run, 1000x kind of performance improvement. And that's all got to be done at the same, if not even in some cases, shrinking power budget. You simply cannot do that with any general purpose architecture that exists today. So DSAs and heterogeneity is the only way forward to meet those kinds of demands. Okay, so let's talk about that a little further. You know, traditional fixed computing architectures, they're really great and flexible for software development, but software is really more in general a procedural kind of, you know, good for procedural kinds of work problems. They're really rather inefficient for the new types of workloads, right? Which most of it is for really power in nature, and again, you need high performance as well as low latency. You know, any given application is not just one uniform thing either, right? You know, typically there's different sub-functions or different types of styles of workload. Be that, you know, you take video streaming, there's certain things you need to do there, you need to process that, and then you might do other kinds of processing on top of that. So this is just trying to represent, if you looked at 3 different types of functions, right? And again, it's not very efficient because you're going back from, you know, the cache to external memory. A lot of times you hear about the term dark silicon. That just means the CPU isn't being used because it's just waiting, it's stalled, waiting for memory to for data to come back. Now you compare that to a heterogeneous architecture. Keep getting ahead. Sorry about that. If you compare that to heterogeneous architecture, then you can pretty much target the different types, aspects of the workload to the appropriate engine, if you will. So if it is procedural and control nature, then it can be targeted to the CPU. If it's something that you know, is a parallel and maybe does a lot of kind of like linear algebra kind of applications, there are vector type architectures that are very appropriate. And then for just general kind of kernel acceleration, you know, we show an FPGA fabric because that's the most general kind of, you know, accelerator that you can implement. You can do various different precisions, you can do different data flows and so forth. Now, if you add adaptability to that, that also means that not only can you target the different engines, but you can optimize those things for the workload that's being processed right at that very moment. And on top of that, you can implement those DSAs as overlay architectures, you know, be that in the FPGA or in other kinds of parallel architectures. So this is why we think that this ACAP, you know, Adaptive Compute Acceleration Platform, is really going to be fundamental in the new era of AI and computing in general, for that matter. So just to refresh your memory, if you've never heard the term ACAP, an ACAP is a silicon architecture that has CPU SoCs, you know, SoC typically multi-core, but it's not necessarily that, an FPGA array. It may also have other types of engines, right? Right now, I'll come back to that AI engine, but it may have other kind of processing engines. But it's all going to be connected together with an on-chip and network on a chip, a NOC. And it still has other programmable, although hardened interfaces for on-chip interfaces, be that memory or serial interfaces. Versal is our first, and for that matter, the industry's very first ACAP. We implemented that in 7 nanometers at TSMC. The first product is 36 billion transistors and change. Believe it or not, that's not even the largest product in the product family, and that is a monolithic chip. That's not what we would call SLRs, or other people now, the term is chiplets. So we will have even larger Versal product family members. Versal is going to deliver anywhere from 4 to 10x the performance and energy efficiency relative to the state-of-the-art 16 nanometer FPGAs that are shipping today. And I would say 10s to even 100x performance relative to general purpose processors for a lot of the applications that are driving AI and the next era of computing. And now I'm going to talk a little bit about this AI engine because it's the AIEra, right? So this is a new architecture, and let me just go into that in a little more detail right now. Okay, so it's a tiled architecture, and the tile consists of the AI engine with some local data memory. Okay, it's 32 kilobytes of data memory. The AI engine is a proprietary superscalar unit that also has a vector unit. In one clock cycle, you do 2 loads, 1 store, 2 scalar ops, a vector op, as well as streaming access the local data memory. Data types include, on the integer side, 8-bit integer, 16-bit, 32-bit integer. 32-bit single point floating point is supported, and the vector unit is 512 bits. The unit could execute 128 8-bit max per cycle. So it's, and by the way, in the implementation style, if you wonder, is this FPGA? No, it's implemented just like you would implement any other kind of fixed function architecture. However, it is still hardware programmable, and I'll go into that in a moment. So it's a tiled architecture. So you take that basic tile, and you step it off in a 2D array. You can do anything from assemblies of 10s to 100s. That first Versal product that I told you that we taped out, and we are sampling the customers, has 400 tiles in the array for that particular family member. It could access, I said in a single clock cycle, it could access the local data memory, but could also access any tiles, adjacent tiles, data memory. But the interesting thing, the part that's programmable, like the engine itself is software programmable, but the additional hardware programmability is the fact that connectivity of the array itself can be programmed, right, to have any topology. Which means that you can take this array and you can implement architectures that are systolic arrays, data flow arrays, pipeline arrays, or any other kinds of different connectivity. In fact, because that's hardware programmable, you can actually change the configuration of the topology dynamically while the product is running. Right? So you don't have to take it down. While it's running, you can actually change some of that so that if you want to accelerate, if an application is running a certain kind of algorithms and then it moves to a different part of the application and you need different types of kernels, you can actually change that dynamically. Or if you just swap out different architecture, different applications altogether, you could implement a different algorithm or neural network. Now the performance and the power efficiency that I talked about, getting factors including 10x, really what it comes down to is not only because you have massive amount of compute density, but because you can architect the memory hierarchy, right? Not only the closely distributed local memories, but the memory to the fabric, the FPGA fabric, and off-chip memory. And I think that's one of the things that everybody missed. Someone's sort of, it's a really bad, I always get frustrated when everybody focuses on TOPS, right? It's not about peak data path performance. Usually you're limited by that memory hierarchy, right? So it's all about data movement, and the thing about this adaptability is you can spatially place kernels and you can change the connectivity dynamically. You can configure the memory accesses within the array to that FPGA and even off-chip. That's really powerful, and that means you could actually sustain a tremendous amount of efficiency, density of this multi-core array, and you can sustain performance as opposed to peak performance, which TOPS numbers are all about, right? So you can optimize this kind of an array for a single application, a domain of applications, or many different applications. So what does this get you? So this shows a fairly recent GPU that's targeted for inference. And I'm going to talk about inference because remember, I'm talking about how over time inference is going to be bigger than training, and inference requires low latency. Right? So that GPU accomplishes about 26,000 images per second with a 2 millisecond latency. And that's important because with low latency, you can't do large batch sizes, which is just a technique for sort of getting larger commute done, but offline, so to speak, with very long latency. Now, Versal, Alveo is the name of our acceleration boards. Versal, we state, is going to be about 9,000 images per second. in 2 milliseconds. And if we add additional techniques like pruning, channel pruning, which we could do with the exact same piece of silicon, then we think we can get another 30% improvement with, again, just using these pruning techniques. And for that matter, that's the other thing with flexibility. If you have new algorithms, new optimizations, you can deploy that because you don't have to change the silicon in order to deploy this. So now you might be thinking this is all great for hardware developers, but what if you're not a chip architect? How can you use the power of something like Alveo, versatile ACAPS? Well, to enable software developers, we just announced this at the XDF. We have a new unified software development platform called Vitis. I'll just very simplified software stack will work from the bottom up. At the bottom you have boards, you have board support packages, you have the runtime, and you have your compilers, profilers, debuggers, and tools. Above that, you have optimized libraries. Xilinx is going to be providing 8 different optimized libraries for things like linear algebra, computer vision, finance, and there'll be others over time. And we interface all the way to industry standard frameworks for AI, like TensorFlow Cafe. There'll be more coming on the line. And within that, there's also DSAs that are supported. There are things that we provide, but we also have partners that provide DSAs to accelerate other types of applications, and also are producing optimized libraries. So for instance, Blacklinks is a partner that has a DSA and some acceleration for Elasticsearch. So let's look at Vitis AI. So since it's an AI talk, I'm going to focus on that particular platform. This is what the Vitis AI platform looks like. Again, we could target the different targets, right? This SoC, we could target different types of networks through these DSAs, domain-specific architectures, that are targeted to accelerate networks like CNNs, LSTM, and others. We also provide tools to optimize the network itself, like quantizers to bring things down to lower precision, right, to save power and space, compilers and profiles and so on. And we're also provide actually a number of reference models. Actually, we're providing I think 30 reference models for different types of fairly commonly used things for things like object recognition, image recognition, and so forth. And then, of course, we interface to these common environments like TensorFlow, PyTorch, and so forth. So this integrates very seamlessly into the general Vitis stack. And some of these tools and optimization tools that I told you about in terms of quantization and other kinds of network optimizations, we see that you can improve performance for any given network. Sometimes we see people getting factors of 10 to even 20x by doing these things without sacrificing accuracy. Okay. So, I apologize. I don't know. Somehow the bills are always bills kill you. All right. So what I wanted to do was give an example of how this would look for someone working in TensorFlow, but now in synchronization nightmare here. Okay, here we go. All right. So I guess there's a lag. Okay. I guess I stepped too far away from this. Okay, finally. All right, so high throughput, we skipped over all these slides. So let's say someone's used to TensorFlow. What they could do is they could use Vitis AI platform and compile that network, and if part of that workload goes to the CPU, it'll get compiled down to the CPU. If part of it goes to the fabric, or if part of it goes to the AI engine. We show an off-chip service CPU because if there's a data center application, we have an FPGA acceleration card. It's obviously some sort of x86 server off chip. But the thing is, basically, the platform will automatically take that TensorFlow model and map it to the appropriate unit. And the other thing that we provide, I mentioned these domain-specific processors. We have something called DNN processing units, or DPUs. And those are overlay architectures that can be implemented in the FPGA fabric as well as the AI engine. And because you compile that into those things only once, After that, when you compile a network into that targeted DPU, you get compilation times of minutes or even seconds. Unlike for those of you familiar with FPH, which oftentimes that could be many, many minutes, even hours to do compilation. So this gives you much more like a software compilation experience because you pretty much have a virtual architecture on top of the hardware, and then you're doing fast compiles to that. Totally deterministic. There's no time enclosure for those who are really familiar with these details, right? So let's look at an application, okay, just give you an idea of how you can map onto something like an ACAP, a versatile ACAP. So this is, let's say this is some sort of smart city application. You have several cameras, multiple camera streams. You're doing some video decode, some computer vision. Then you have some sort of ML for detection. You track the objects. Then you have another ML for network for the classifications. And then you do some other analytics and perhaps pass that on metadata into the cloud. This is just showing how these different steps in this data flow from left to right can be mapped to different parts of the ACAP. So the AIs, again, obviously that maps to the AI engine. And you can map the video processing and computer vision aspects, as well as the object tracking into the FPGA portion or the multi-core ARM SoCs. The video analytics management and maybe ingestion could be, in this case, is shown being done by a server. And if that's the way the configuration is, because you just have the ACAP as an accelerate card, that's how it works. But really, we can also push that processing into the ARM chip, so you could really, if you really think about it, what we're really doing is pushing processing to the edge from a cloud configuration, right? And I think we, like many other people, see that a lot of processing is going to be moving to the edge, right? And Vitis AI helps you do all of this. You could work, again, in cloud-based applications where there's a remote host, and you could also work if it's all embedded in a device. So, in general, what we're sort of seeing is that, there is a lot of trend, as I said, from the cloud to the edge. And usually when you're doing that, it's because you need much better real-time response, very low latency, and also perhaps because you don't want to have very high bandwidth requirements from the edge to the cloud. It can also be for things like privacy or security or things of that nature. But actually, we also see it going the other way around, that we see sort of local edge processing being pushed in the cloud. Why would people do that? Well, often that's being done to get scalability, right, and low TCO by processing things in the cloud and getting more resources and things on demand. So we actually see a tremendous amount of experimentation, if you will, across the whole gamut from endpoint to edge to the cloud. So, and again, because of the flexibility, we support models where you could have, before those cameras were all dumb, now you can look at you do some of the processing at a smart endpoint, right, where you do some of the encode there, and then you do most of the rest of the processing at the edge, and you can send just metadata up to the cloud. But you could also have a different configuration where you could do more intelligence at the endpoint. In fact, you can get rid of the edge, right? You can just have intelligent endpoints going right into the cloud. In fact, we have some customers that actually really need to deliver all three of those kind of configurations to their customers. And that's because different customers have different needs, or they have different already existing investments, and they want to deploy this kind of technology and architecture in those different configurations. So our customers might need to support all three configurations, but they don't want to have to do point solutions for all three. And that's the beauty of our platform, because we can support all of those configurations, right, with the adaptable solution. So here's another real example. I don't know how many people know YY. Anybody know the company YY in China? So they actually have 300 million users. I guess it's some type of social kind of platform with video and all kinds of things like that. I'm too old to understand any of that. I just know that they need a tremendous amount of processing capability and low latency and everything else. So anyhow, what they do is, it's kind of like the first example, except instead of cameras, these are people's mobile phones, right? So all the users, 300 million strong, they take they decode H.264, they're doing some analytics, they're processing that, and they encode in HEVC. Right now, their data center is just all, Intel processors. I mean, that's, again, we're in the very early stages. Most people still use CPUs for virtually everything. But they had a problem because they were growing users so fast, they just couldn't scale the data center fast enough. They didn't have enough power, they didn't have enough rack space. So there's a partner of ours called AIEra, and they did a really disruptive platform here. And that one platform has 48 16 nanometer zinc FP SoCs. Each one of them does have a video codec, and these things obviously have the SoCs as well as the FPGAs. And with that platform, they use some of the Vitis AI technology I showed you, and they created their own custom video processor for the analytics. And so this platform replaces 30 E5 servers. So the performance is 3.3x those servers at 1/10 of the energy and 1/10 of the rack space in the real estate. So this is really, truly disruptive. And remember, since it's flexible, if they have new algorithms, if they have a new codec they want to deploy, they can deploy that with the same hardware. So we are working together with YY and AIEra to help them deploy this in their data centers. Keep getting too far away. So if we talk about data centers in general, those are a couple of specific cases. This is our view of the future of the data center. We kind of just put this handle on it that we call distributed adaptive computing. And the idea is, instead of the traditional compute structure, and also, by the way, where you have all the computing happens in the CPU or maybe a near accelerator card, all the storage is storage, and then the network just does networking. Really, we think that the way to think about it is the entire data center is sort of the computer. And what you want is CPUs attached to that network with smart NICs that could, based on ACAPs, today it could be based on FPGAs. You want computational storage, so if it makes sense to do processing near where the data is stored instead of moving it back across and creating network traffic, you can do processing near the storage. You could also do things like compression and dedupe and other things. And then, just for compute acceleration, you could have pools of homogeneous accelerators rather than acceleration just for fixed functions, right? And the beauty of that is that, okay, you have a very homogeneous architecture, but they can still be customized. So if you have an application, if you had a first workload that really is using a lot of network intensity, then you would want to use some of those resources. You would provision to that workload the resources that have CPUs with smart NICs. Smart NIC can offload the networking functions so that network bandwidth is not throttled, the CPU cycle gets freed up for that, and you can do processing at line speed as well, right? If you have an application like AI that needs more compute, you would just assign it more ACAP compute accelerators, and you would optimize the compute for whatever neural networks that you're trying to accelerate. And they had some sort of data analytics, then you would assign it perhaps maybe more computational storage elements, right? And again, you could provision on the fly, and you can customize all those accelerators wherever you need acceleration. Near the CPU, near the network, near the stored data, right? We think this is an incredibly powerful model because in the end, what this then provides operators, the values that this provides data center operators is low TCO because you get very high utilization of those on-the-fly customizable accelerators, right? And the accelerators do much better in terms of performance per watt and everything, right? The other thing is you get both high performance and low latency, because remember, ACAPs, FPGAs are very good at getting throughput performance and still with low latency. And then finally, you can customize and deploy new codecs, new neural networks, new algorithms to accelerate neural networks like pruning and quantization without changing silicon, right? So you're not throttled by silicon cycles, either if you have your own proprietary team or if you're counting on merchant silicon, they just have a pipeline of roadmaps. You can deploy in this flexible hardware at any time. Right? Okay, so I'd actually just like to end with an application of AI inference in an application that is really intensive in terms of AI, right? This is fully autonomous driving. I don't know if you know this company, Pony AI, that they're a very innovative startup. They actually have a location just down the street here in Fremont, I believe, right? And also in China. And so they're doing self-driving cars for the future. And as you might know, the conditions, the complexity of doing autonomous driving is incredible. The scenes change very rapidly. Obviously, it's safety, so you can't have any errors because it's literally a matter of life and death. So I'm just going to show you a video This is from Pony AI. It may take a little bit of time. And so we're looking at the perspective of the white car, and this is traffic at night in China. And you can see all these different objects, people's cars, bicycles, motorbikes that all have to be tracked and watched. And it won't move until it sees a safe way to move. Then it's showing you tracking lanes, looking at objects and the scene in real time. And this is processing all that data in real time. Again, I guess you could just watch for yourself. You can see having to do dynamic routing. As it's trying to move, it's trying to find a safe path, but then all the objects are moving. So again, huge amounts of very different types of data. By the way, there are some companies that use mainly video. Yeah, this is in China, right? So those of you who've driven to China, it's difficult for human intelligence, let alone artificial intelligence, right? And what's even really harder is rain, right? So I was just going to get to this. There are some systems that use video cameras only, but that's very difficult in conditions like rain or snow or other things. They use multiple sensors, LiDAR and multiple cameras. And one of the other things about FPGAs and ACAPs is that we can also do sensor fusion because we have such programmable interfaces, and you can have flexibility. And again, real time, right, at line rate kinds of interfaces. And then we could also process the AI. So it's really pretty impressive technology. They were at our developers forum as well. They're using some of our current technology, and they're working on Versal. Very interested in using that and broadening the use of our products in their technology. So really exciting, just one instance of one of the applications and very germane to AI. So, just to wrap this up, as we enter AI, we really believe that computing, adaptive computing is needed and will emerge in this new era of AI. And again, it's going to play a very large role in computing in general. And on top of that, Versal ACAPs really empower more innovators, especially with us releasing things like Vitis, right? Historically, Xilinx's customers were hardware developers, but by creating that software stack that goes all the way up to things like TensorFlow, right? We have deployment with Docker, Kubernetes for large deployments, scale deployments. We're doing everything that you would for any other kind of, target like a CPU or GPU. And what we're going to do is hide that power of customized hardware acceleration underneath the hood, so that it's not just hardware developers we can support, we can enable software developers, we can enable data scientists. And I think that's really exciting because I think that really democratizes innovation in AI, and it will accelerate innovation because there'll be more people that could use this really powerful, adaptable platform to achieve things like 100x kinds of improvements without needing $100 million kinds of capital investments, or perhaps waiting for other merchant suppliers to go through a very fixed and less flexible solution. And so we think it's a really exciting time. Again, I think everybody's probably used AI today multiple times. And in just 5 years from now, I think it's just going to be in every facet of our lives. Whether it's fully autonomous cars that consumers have or robo-taxis. I think robo-taxis and things like on campuses will definitely happen. Heavy equipment, trucking, and so forth. So it's really going to happen, and we're absolutely passionate about making a big contribution to the era of AI and computing in general. So thank you very much.